I'm Charles H. Bennett. I work at IBM Research. I'm an IBM Fellow, and my field is the physics of information processing. The ACM Turing Award is important because it establishes the importance, both in theory and in practice, of studying the physics of information processing. My parents were music teachers, and I was always interested in science from about 2 years old. At first, I was interested in biology. I was growing up around the time of the discovery of DNA and the double helix and so on. Went to university in Brandeis University, and while I was doing that, I got interested in the mathematics of chemistry, or essentially physical chemistry. So I ended up going to graduate school again in physical chemistry, chemical physics. I was a teaching assistant, and so we were teaching about the genetic code, and at the same time we was learning about Turing machines, which were the first formalization of the process of computing. So I started thinking about the physics of computing. So that's how I got started in that direction. But then around that time, Rolf Landauer, who worked at IBM, came to visit me, and he had just written something about why it is that computers need to consume energy and convert it into waste heat. And he argued that there are some operations that necessarily do that, and some others that don't need to do it. They may do it, but it's not essential. So I started working on that, and then he recruited me to come to IBM, which I guess I came here in the early 70s, and I've been here ever since. I was very excited by this place because in this building, there were people who were working on fundamental physics, which is necessary to build the hardware of computing, the transistors and so on. And there were in the same building people who thought about the mathematics of computing. And I could wander down the hall and talk to many people about ideas that were fundamental and in fields that at that time scarcely overlapped. Gilles Brassard and I got this award for being among the early founders of what's now called quantum information theory. Quantum information theory is a theory that enlarges the ordinary theory of information that people understand in a very elegant way. Quantum information is more like the information in a dream. If you tried to tell somebody what you dreamed, you forget the dream and you begin to remember only what you said about it. And you can't prove to somebody what you dreamed. But unlike dreams, quantum information follows well understood laws. And it turned out to be useful for some things. Teleportation. That was another thing that developed a lot of interest in. There were 6 people who collaborated on the teleportation paper. I think Gilles counted it as 26 papers we wrote, but with a lot of co-authors. So we sort of got this field started, but now there are hundreds of people working on it, and they're doing things that we scarcely even understand anymore. I met Gilles at a conference because he had written a paper related to a paper that I had submitted to the conference and had been rejected. I met him in the ocean. We were both wearing bathing suits. The conference was held in San Juan, Puerto Rico, and we were recreating on the beach there. And I said, oh, that's Brassard. I wanted to talk to him about that. So I swam out to where he was and started talking to him. And we both got excited enough about that we came into shore and started writing things down. The first thing that we did that was potentially useful is develop what's called a quantum key distribution or key exchange or key agreement, which allows 2 people who are communicating by a quantum channel and also by an unjammable public channel, like you and me talking together. We know that what you say I hear, what I say you hear, and what I think I hear you say was said by you and not by somebody else. So that's an unjammable public channel. If you have those features, 2 people can come into agreement on a shared secret that nobody else knows. And that is the root of some of the most important kind of cryptography. John Smolin was an undergraduate assistant with me. He worked in my office and largely built the apparatus that was programmed by Gilles, which was the physical implementation of our BB-84 idea. So he was intimately involved, but the field has really grown in a way that we're very pleased with. I think everybody should have an understanding of quantum information at the level that they do of relativity and of black holes. In other words, they can't do calculations or write papers about it, but the ideas they've developed a rudimentary intuition for the most important ideas. And I think being able to do these things on an actual physical computer helps. And of course, the other thing it does is get a lot of people trained to be ready to use more functional quantum computers when they are eventually, and I think inevitably, become available.